And next, we will move on to the massive MIMO. So to explain about the massive MIMO, as I said earlier, we will be using the more number of antennas there. So first, we want to see what is the evolution of MIMO in a simple terms. In the simple term, we will try to compare what MIMO was before. Okay, initially it was point-to-point MIMO that is identified by Paul Raj. Initially it was point-to-point MIMO. So we have a base station which is equipped with the multiple number of antennas, and we have a basically our mobile phone cannot have more than one antenna. I recently heard that some phones are coming with the MIMO capability. So imagine, because of that wavelength and all those things, our phone cannot accommodate more than one antenna because it has to be separated by a distance of lambda by 2. So literally, MIMO scenario is impossible. So consider there is a MIMO scenario, a virtual MIMO scenario, like within the lab. So here we need to transmit multiplex the information from a base station to the receiver. Transmitter is equipped with multiple number of antennas, and the receiver is also equipped with multiple number of antennas. Here it is a little expensive, firstly, because we need to accommodate more number of antennas within a small device. And MIMO, point-to-point MIMO, is literally a failure there, actually, because of its cost, firstly, and also for pre-coding, we require CSI at both transmitter and the receiver. Only if the CSI is available at the CSI is channel state information. Only if the channel state information is available at the transmitter and the receiver, then only this point-to-point MIMO will have some value with it. Else, actually, it is used. But estimating the CSI is a huge task, and we will know in the next slide. We will know why point-to-point MIMO is a failure. Okay, so this is one thing about the point-to-point MIMO, and particularly this is not preferred in the communication because of its expensive multi-antenna terminals. Okay. And the next one is multi-user MIMO. In the point-to-point MIMO, we have multiple antennas in the receiver within a single device. Now, consider each device is having, anyway, each mobile device will have one antenna. So there are many number of such devices are there, like our mobile phone. So there are many people who are having the mobile phones. Everyone will be combinedly acting as a MIMO system. They will be combinedly acting as a MIMO system. That's why it's called as a multi-user MIMO system. Okay. So there also we require a CSI, but the CSI estimation is a little easier there because we don't have to measure a complete matrix. Like for the previous case, if we go for the channel matrix, there will be the matrix size will be m cross n based on the number of transmitter and the receiver antennas. Whereas here, number of transmit antennas only matters because the receive antenna is only one. Ultimately, your channel matrix is only a vector there. So for the multi-user scenario, the CSI is not a big deal, but still the CSI has to be estimated at both the ends. Okay, so this uses dirty paper coding as well because decoding will be a little bit easier with the dirty paper decoding, and it should be noted that the number of transmit antennas should be almost equal to the number of receive antennas. So if I am serving 10 number of users, it should have at least 10 antennas at a time. Okay, but in real life, if the base station is having 100 antennas means, then simultaneously it can serve 100 members. But anyway, this 100 members will make a call or not. That is a big question. So anyway, this number of antennas won't be a matter here in the case of multi-user MIMO, and this gives a same theoretical gain like our point-to-point MIMO, and we have to deal with the interference as well. Okay, so this is about the multi-user MIMO scenario, and we will move on to the massive MIMO scenario. Okay, this is a LTE advanced base station. Right now, this is the LTE advanced base station that is using a multi-user multi-user MIMO scenario. Okay, so this is a within one site. We will be having 192 antennas, and each site is constructed with the number of sectors. So totally there are 64 antennas per sector. One sector will have 64 antennas. Overall, there are a lot of antennas will be there. So this is the base station for LTE advanced standard, and some wiring changes actually will help in going for 4.5G or something. Okay, so this is purely a 4G technology, and some wiring based on beamforming and digital beamforming, analog beamforming like that, and some signal processing changes will actually yield a 4.5G kind of communication. That has been also been done so far, and we will quickly move on to this massive MIMO. So in the massive MIMO, the difference is the antennas are very much higher. The transmit antennas are very much higher. Okay, and the main thing with massive MIMO is in the receiver side, we don't have to estimate the CSI at all. Okay, the channel state information is not at all required in the receiver terminal. Because why? Because all those signal processing tasks will be done by this base station. Base station is a huge unit. Definitely it can help in this signal processing. It will do the signal processing and CSI estimation, everything. It will be estimating the CSI including the users. Okay, it will not just calculate the CSI for his own transmission, but it also helps the user to get the transmission. Okay, so in this way, this massive MIMO will be helping us, and particularly this massive MIMO will have more than 100 to 200 antennas. That's what it is planned, and it can be installed in any buildings or anything. Okay, so inside the buildings, inside the infrastructure, we can have that multiple antennas. So the way the communication is going to look will be completely changed in future. And this CSI, what happens with this massive MIMO is, as the number of antennas increases, the directivity is also getting increased. So what happens is, as the directivity increases, it can reach any part of that, any part of the village or anything, any part of the area. Like if some areas are not having proper coverage, so when I go for this massive MIMO, that particular area will be concentrated, and the beamforming is done towards that particular area, and definitely that will help in complete coverage of the country, right? So in this way, this massive MIMO is contributing to this 5G technology. This is one of the main candidates with 5G technology. Okay, and the main thing with this, your mobile battery will not be wasted for estimating the channel state information. So everything will be done by the base station itself. Okay, in that way, this massive MIMO is being defined, and as Mazarata said, channel state information isn't everything. It's the only thing. It's the only thing that is available to communicate with the users. So CSI will be available with only the transmitter base station. Right? And to explain little more, a simple mathematics equation can explain about this massive MIMO very well. Okay, so let's assume that I have a MISO. MISO means a multi-input single output system. That means multiple antennas are transmitting and only one guy is receiving here. So here we have the receive equation as y is equal to summation of m equal to 1 to 4, because 4 antennas are being transmitting the same signal. I mean the different signal, sorry, x1, x2, x3, x4, and those things will be multiplexed and will be reaching the destination here. So y is nothing but the linear combination of signal and the channel coefficients. Okay, so in this way MISO can be explained, and also there will be a noise term there, right? And let's go for a matched filter scenario, where we will be having the matched filter here. This W1, W2, W3, W4 are matched filter. So what it means is, when I am sending a signal, that particular signal will be multiplied with this matched filter coefficient W1, and W2, W3, W4, and these signals will be multiplexed and being received in the receiver. For that, the equation is everything is a vector here. Remember, everything is a vector here. So H transpose H star divided by norm of H is the beamforming vector we are using. This is literally a beamforming. When you are multiplying with the coefficient, that is a beamforming, because we are multiplying with the beamforming vector, and this beamforming vector is defined by H conjugate. H star means H conjugate divided by norm of H, and while transmitting, this S will be multiplied with the H star divided by norm of H, and while transmitting through the channel, H transpose will be added while transmitting through the channel, and the noise will be getting added. Ultimately, our equation will be like this. This is the final equation here. Norm of H into S plus N. Yes? Hello? Okay. Ma'am, anything disconnected? Hello? Am I audible?
Yeah, yes, sir. Continue.
Yeah. Somehow the screen is getting popped up. I don't know why. Okay, fine. Okay, now we have a SNR. That is the signal square, the signal coefficient square divided by the noise power. So we will be having that norm of H square into sigma A square is signal power. That is a signal power term, sigma A square. Similarly, we will be having a noise power term here. So if you see that this SNR can be improved, by improving the number of antennas, by increasing the number of antennas. Don't know somehow. Yes. So yes, any problem with the line? I'm getting the screen popped up often.
No, sir. So can you change the slide once?
Actually, this team, that app is getting popped up often. I don't know why. So we have the SNR here, and this SNR is improved by increasing the number of antennas M, so that our SNR will be improved. So as the number of antennas getting increased, this SNR will also get increased. That's what I am trying to say. So this beamforming vector, using this beamforming vector at the transmitter, and by increasing the number of transmit antennas, we could able to achieve a better SNR. So this is one thing with the MISO system, and the next one is multi-user MIMO scenario. So this is the real scenario. That is an imaginary scenario, because one base station is not going to serve one particular guy. So this is the real time scenario, right? So we are having 3 antennas, and everything will be right now. I am just considering the link from the antenna 1 to all the 3 users. That is H1, H2, H3. So these are all the vectors, because we are transmitting from the multiple antenna scenario here. Okay. So this is also a linear combination of channel coefficient and the transmit symbol. And this transmit symbol, we have to notice that this transmit symbol has all the three users information. This 3 user, K is the number of user here, and K is the number of user here. So we have multiplexed that 3 users data, and that will be transmitted through the channel H. The thing we have to notice is for user 1, user 2 and user 3 are interferences only. For user 2, user 1 and user 3 are interferences only. So we don't have a SNR here, only for that particular user that will be decoded, and the rest will be considered as interference only. Say I am a ith user. Ith user will be getting only his data by multiplying his own channel coefficients, right? So likewise, when we are multiplying this Hj, I mean other users data, when it is getting multiplied with our channel coefficients, then there will be out of sync. They will be out of sync with that. So what happens is, naturally interference, this is the interference term, interference will be generated. So SINR will be given by SINR is given by signal power to that of the interference and noise power. So this is very bad actually. So in the multi-user MIMO scenario, we will be serving more than one user, and we will be having this interference term. This interference term is very crucial. So I am just blocking this. Okay, this term is not there with the single user scenario. Anyway, in real time, this term is always there. Okay, this is with multi-user MIMO. Okay, what this massive MIMO guy is going to do is, so as the number of antennas increases, this SINR will also increase. SINR will also increase. That literally means that this interference term here will actually tend to 0 as the number of antennas M goes to as the number of antennas M is equal to 100 or 200 or something, right? So as the number of antennas increases, this guy will be keep on increasing. Yes. Somehow this Teams window is keep on popping up. I don't know why. Can someone help me? Yeah, Praveen or someone?
Yes, sir.
This Teams window, right? That
Yeah.
Microsoft Teams. That window is keep on popping up in front of my screen. Is there any way to block that? I don't know. Maybe someone is leaving, someone is going out, someone is coming in. I don't know. Okay, fine. Now it is okay. Maybe when I'm presenting, it is getting fine. Okay.
Sir.
As the number of antennas increases, the interference term will literally go to 0, and
Hello, sir.
Yes.
Yeah, your voice is not audible.
No, I don't know. It is getting popped up often.
Yeah, now it's okay.
Okay. See. Any way to block this? Okay. Yes, 1 minute. 1 minute. Okay, fine. So this is what about this massive MIMO. And as the M increases, this term will be tending to 0. That means SINR will be now converted to SNR alone. Okay. So in this way, massive MIMO works, and this will definitely be a revolution in 5G and beyond. And massive MIMO is coming up. Okay. So also, our mobile also can have more number of antennas there, because the operating frequency is very large. This lambda will be very small, so that we can keep that antenna more number of antennas within a small device itself. Okay. That is about massive MIMO, and this is the number of antennas and directivity and its directivity. If I am using only one antenna, then it is actually omnidirectional. It will transmit in all directions. Here M means the number of antennas here. Okay, and once the M is equal to 8, M is equal to 8 means 8 number of antennas will be there. So the directivity will be somewhat there, but still there will be some side lobes that will cause interference to the nearby users. Here, this nearby users here, there will be some problems because of that my side lobes. And when we are having the number of antennas more than 64 or 100, this beam will get narrow and narrow, so that we don't have any side lobes, and the desired user alone will be particularly served there. Okay, so this will also prevent leakages to the nearby users and causing unwanted interferences there. With the number of antennas, the directivity is actually very well improved. Okay, and these are all some applications of massive MIMO. Firstly, what actually